Welcome back to this module on dynamic exploitation of ILP. The topic of this lesson is multiple issue processes. So far I have focused on single issue processes, processes that issue a single instruction per cycle. The ideal CPI of such a processor, even if it dynamically schedules the instructions and performs speculation, is 1. So it's natural to ask, how do we break the CPI equals 1 barrier? How do we achieve a throughput of more than one instruction per cycle? This question is the motivation for this lesson, in which I discuss multiple issue processes. Processes that issue but also fetch and execute multiple instructions each cycle. There are 3 major types of multiple issue processes. The first one is dynamically scheduled superscalar processes. In such processes, hazard detection is performed in hardware and instruction scheduling is performed dynamically in hardware. They are called superscalar because they execute multiple scalar instructions per cycle as opposed to vector processes, which also perform multiple operations, but these operations are vector instructions rather than scalar instructions. Dynamically scheduled superscalar processes are the topic of this lesson, and all modern desktop processors such as the Intel Core i3, i4, i5 and i7, the AMD Phenom and the IBM Power 7 belong to this class. The second type is very long instruction word processes. In such processes, hazard detection is performed primarily in software by the compiler. Furthermore, instructions are not dynamically scheduled but executed statically. I will discuss VLIW processes in the next lesson. The third type of multiple issue processes is statically scheduled superscalars. In such processes, hazard detection is performed in hardware, as in dynamically scheduled superscalars, but groups of instructions are executed in order. Recent MIPS and ARM processes, such as the ARM Cortex-A8, belong to this class. Such processes are, in fact, very similar to VLIW processes, and I will not discuss them separately. I will now discuss some implementation challenges of multiple issue superscalar processes. First, a superscalar processor needs to fetch multiple instructions each cycle. This is highly complex since the instruction stream contains branches. In other words, consecutive instructions in the instruction stream are not necessarily consecutive in memory. I will return to this issue in a few lessons when I discuss how to increase the instruction fetch bandwidth. Second, a superscalar also needs to dynamically issue multiple instructions each cycle from the instruction queue to multiple reservation stations. This is probably the most complex implementation challenge, for the simple reason that the multiple instructions may depend on each other. For example, if the second instruction is data dependent on the first, then the first instruction will update the reservation station field of its destination register, and the second instruction should be issued together with the identifier of that reservation station. 2 approaches have been used to solve this problem. The first is to pipeline the issue logic and to execute each stage in half a clock cycle, so that 2 instructions can be issued in 1 clock cycle. This does not scale to more than 2 instructions per cycle, however. The second approach is to widen the issue logic so that 2 or more instructions can be handled in parallel. But since the instructions may be dependent, parallelizing the issue stage is far from straightforward. Modern superscalar processes that issue 4 or more instructions include both approaches. They both pipeline and widen the issue logic. Another implementation challenge of superscalar processes is that they need multiple operation and operand buses and also multiple read ports to the register file. An n-issue superscalar processor typically requires 2 n-read ports to the register file. The area of the register file, however, grows with the square of the number of ports. In current technology, around 12 ports, 8 read ports and 4 write ports are feasible. The final implementation challenge I would like to discuss is that we need multiple result buses to be able to complete several instructions per cycle. In other words, the common data bus needs to be widened. Furthermore, each reservation station will require multiple comparators in order to determine if it is waiting on any of the results produced in a single cycle. Hopefully I have convinced you on the previous slide that implementing a wide issue superscalar is very challenging. In the remainder of this lesson, I will show how a loop is scheduled on a dual issue superscalar without and with speculation. The example loop is shown here for completeness, adding a scalar to all elements of an array X. We have seen this example several times before, so there is no need to discuss it again. This slide summarizes the hardware assumptions. The loop will be executed on a dual issue superscalar that can issue and complete 2 instructions per cycle. The remaining assumptions are identical to the assumptions made before when I illustrated dynamic scheduling. For completeness, there's one integer functional unit that is used for ALU operations as well as effective address calculations. There's a separate functional unit to evaluate branch conditions, so branch conditions are not evaluated using the integer functional unit. There's a separate pipeline floating point functional unit, and I assume that both the issue and the write result phase take 1 clock cycle each. And as before, I assume perfect branch prediction. Furthermore, first I will assume no speculation. That means that predicted instructions are fetched and issued, but not executed until the branch completes. Later on, I will show how the loop executes when speculation is supported. Finally, this table summarizes the execution latencies. As before, 1 clock cycle for an integer ALU, 2 for a load since it consists of effective address calculation and a memory access, and 3 clock cycles for a floating point addition. This table shows for each instruction the time of issue, execution start, memory access if applicable, and the time at which the CDB is written. I will now explain why the loop is scheduled as indicated. First, 2 instructions are issued per cycle since we assumed a dual issue processor. So the first 2 instructions are issued in clock cycle 1, the next 2 in clock cycle 2, etc. The first instruction does not stall since it is the first one that is issued. So it issues in clock cycle 1, executes in clock cycle 2, accesses memory in clock cycle 3, and writes the CDB in clock cycle 4. The add double has to wait for the preceding load to write its result on the CDB. So it starts executing in clock cycle 5, executes in clock cycles 5, 6, and 7, and writes its result in clock cycle 8. The next instruction, the store, can start executing effective address calculation in clock cycle 3, but the memory access has to wait for the add double to complete in clock cycle 8, and then in clock cycle 9 the memory access can take place. The next instruction, the add immediate, issues in clock cycle 2. However, it cannot execute until clock cycle 4 because the integer functional unit is busy calculating the effective address of the store in clock cycle 3. So it executes in clock cycle 4 and writes the CDB in clock cycle 5. The branch is issued in clock cycle 3 but has to wait for the preceding add immediate to complete. The branch therefore executes in clock cycle 6. The load from the second iteration is issued in clock cycle 4, even though only 1 instruction was issued in clock cycle 3. This is because I assume that the load can only be issued 1 cycle after the branch whose predicted target instruction it is. This is a reasonable assumption. The execution of the load has to wait for the preceding branch to complete since I assumed no speculation. The effective address of the load is therefore calculated in clock cycle 7. The next add double again has to wait for the preceding load. It executes in clock cycles 10, 11 and 12 and writes the CDB in clock cycle 13. The store double also has to wait for the branch to complete, and in clock cycle 7 the integer functional unit is busy calculating the effective address of the preceding load. Therefore it executes in clock cycle 8. Furthermore, its memory access stage has to wait for the result of the preceding add double and therefore takes place in clock cycle 14. The add immediate cannot execute in clock cycle 8 because, again, there is a structural hazard with the preceding store. The add immediate thus executes in clock cycle 9 and completes in clock cycle 10. The branch again has to wait for the preceding add immediate, and finally the load from the third iteration again has to wait for the preceding branch to complete since our processor does not support speculation. I now want to calculate the IPC achieved by our code example on our dual issue superscalar processor without speculation. IPC? Didn't we use CPI before? Well, IPC, instructions per cycle, is just a reciprocal of CPI. Since the rise of superscalar processors, many researchers report IPC instead of CPI, so don't be surprised if you see it in a research paper. First, I observed that a new loop iteration consisting of 5 instructions is fetched and issued every 3 clock cycles. So we might be tempted to think that the IPC is 5 divided by 3, which equals 1.67. However, if we look more carefully at the table on the previous slide, we will observe that 10 instructions start executing every 11 cycles. So the IPC equals 10 divided by 11, which equals 0.91. If we would schedule more than 2 iterations, then we would see that the IPC approaches 1. So even though our superscalar processor can issue 2 instructions per cycle, the achieved IPC is only 1. Furthermore, because more instructions are issued every cycle than executed, the issue unit will eventually fill all reservation stations and stall. For comparison, the IPC achieved by our example loop on a single issue processor was 0.71. So the dual issue processor achieves higher performance, but maybe not as much as we might have hoped. Let us now consider how we can improve our dual issue superscalar processor to achieve higher IPC. First, observe that because there is only one integer ALU, we lose 1 cycle every iteration. Because the integer ALU is busy calculating the effective address of the store, the add immediate must wait 1 clock cycle. So the performance can be improved by adding an extra integer ALU. If we do so, the IPC will improve to 1.25 if we schedule 3 iterations. However, there is also a 2-cycle penalty every iteration because of the control hazard. Because we perform no speculation, the load cannot start executing in clock cycle 5, but must wait for the preceding branch to complete in clock cycle 6. Exactly this is the motivation for speculation, where we start executing the predicted instruction before knowing if the prediction was correct or not. This table shows the time of issue, execution, read, access, CDB write and commit of the instructions in our example loop on a dual issue superscalar processor with speculation. Notice that an extra column labeled commit has been added, since there is this extra phase when speculation is supported. Also notice that the memory access column has been renamed to read access. This is because stores take place when they commit. I will now explain the times in this table. As before, the first instruction incurs no stalls since it is the first one issued. The add double starts executing in clock cycle 5 because it has to wait on the preceding load. Notice that it doesn't have to wait until the load has committed, but only until the load value has been placed on the CDB. The store commits in clock cycle 9. I can only commit after the value to be stored has been placed on the common data bus, which happened in clock cycle 8. The add immediate cannot execute in clock cycle 3 because the integer ALU is busy calculating the effective address of the store in that cycle. Furthermore, it commits in clock cycle 10 even though its result is available long before. This is because instructions commit in order. Furthermore, because our superscalar is dual issue, we assume also that up to 2 instructions can commit each cycle. The branch has to wait for the preceding add immediate. It therefore executes in clock cycle 6. The load from the second iteration is issued in clock cycle 4 and its effective address is calculated in clock cycle 5. So it incurs no execution delay thanks to speculation. The add double from the second iteration again has to wait for the load, and the next store again has to wait for the add double before it can commit. The add immediate again has to wait for the ALU to become available, and the branch has to wait again until the result of the add immediate has been placed on the CDB. And finally, also the load from the third iteration incurs no execution delay, but is executed speculatively. Let me now calculate the IPC achieved by our dual issue superscalar processor with speculation. By looking at the last column, highlighted in red, we see that 5 instructions commit every 3 cycles. So the IPC is 5 divided by 3, which equals 1.67. Of course, there are some startup effects in the beginning, but if we schedule many iterations, the startup effects will be negligible. Furthermore, we cannot improve this IPC by adding an extra integer ALU. This is because the add double in every iteration has to wait for the preceding load and writes the CDB in the same cycle as the load commits, as highlighted in dark red. So the add double will always commit 1 cycle after the load, and therefore we will always lose 1 cycle per iteration. For comparison, the processor without speculation achieved an IPC of 1, and with an extra adder it achieved an IPC of 1.25. So speculation clearly helps. This completes this lesson. Thanks for watching. In the next lesson I will discuss how the instruction fetch bandwidth can be improved. Stay tuned.